This is Shrikot Mujumdar. In this lecture, we will discuss Heisenberg uncertainty principle. This topic falls under the module Quantum Mechanics in MAKAUT syllabus. Learning objective: to acquire working knowledge of the quantum mechanics postulate on the physical systems. Heisenberg uncertainty principle. It states that only one of the position or momentum can be measured accurately at a single moment within the instrumental limit, or in other way it can be stated as it is impossible to measure both the position and momentum simultaneously with unlimited accuracy. Delta x with the uncertainty in position and delta px with the uncertainty in momentum, then delta x delta px greater than equal to h cut by 2. H cut represents h by 2, where h is equal to Planck's constant. Its value is 6.624 10 to the power minus 34 joule second. The product of delta x and delta px of an object is greater than or equal to h cut by 2. If delta x is measured accurately, that is, delta is very small, it is tending to 0. That means delta px tending to infinity from this formula. If delta px is equal to h cut by 2 by delta x, if delta x tending to 0, delta px tending to infinity, as delta x be in denominator part of the right hand side. So delta x tending to 0 means delta px tending to infinity. This principle applies to all canonically conjugate pairs of quantities in which measurement of one quantity affects the capacity to measure the other, like energy and time. Here energy time uncertainty is delta E delta T greater than equal to h cut by 2, and angular momentum angular position uncertainty is delta L delta theta greater than equal to h cut by 2. So we have to remember these three uncertainties. One is delta x delta px greater than equal to h cut by 2. Second one is energy time uncertainty delta E. First one is position momentum. Second one is energy time delta E delta T greater than equal to h cut by 2. And last one is angular momentum angular position uncertainty delta L delta theta greater than equal to h cut by 2. Determination of the position of a particle by a microscope. Suppose we want to determine accurately the position and momentum of an electron along x-axis. Using an ideal microscope free from all mechanical and optical aberrations, the limit of resolution of the microscope is delta x is equal to lambda by 2 sin I. Here I is the semi-vertex angle of the cone of rays entering the objective lens of the microscope. Delta x is the order of uncertainty in the x component of the position of the electron. This is the recoil electron. This is the recoil electron. The photon is incidenting on it and it becomes scattered and making an angle I, and it is falling onto the objective lens. We can't measure the momentum of the electron prior to illumination. That means before the light is falling on the electron, we can't measure the momentum of the electron. So there is an uncertainty in the measurement of momentum of the electron. The scattered photon can either enter the microscope anywhere between the angular range plus I to minus I. If this one is plus I direction, so this one is minus I direction. The momentum of the scattered photon, according to the de Broglie hypothesis, P is equal to h by lambda, where P represents momentum, h is the Planck's constant, lambda is the wavelength of the light used. Its x component can be given as delta px is equal to 2h by lambda sin I. The x component of the momentum of the recoiling electron has the same uncertainty delta px. It will definitely follow the conservation of momentum. The product of uncertainties in x component position, x components of position and momentum for the electron is delta x means lambda by 2 sin I, delta px means 2h by lambda sin I. So delta x delta px is equal to lambda by 2 sin I into 2h by lambda sin I. So delta x delta px is equal to h greater than equal to h cut by 2. Why h greater than equal to h cut by 2? Greater than h cut by 2? H cut means h by 2 pi. So h, its value is small. Dividing by this 2, again 2 pi. So h must be greater than h cut by 2. This is an agreement with the uncertainty relation. Applications of Heisenberg uncertainty principle. Number 1. Non-existence of electron in nucleus. Order of radius of an atom is almost equal to 5 into 10 to the power minus 15 meter. If electron exists in the nucleus, then delta x max is equal to 5 into 10 to the power minus 15 meter. That means is uncertainty in between the radius of the atom. So delta x delta px greater than equal to h cut by 2. So delta x max delta px max is equal to h cut by 2. Delta px is equal to h cut by 2 delta x. Putting the value of delta x here, this one becomes 1.1 into 10 to the power minus 20 kg meter per second. Then after calculating the energy, E is equal to delta P into C. We are writing here P into C. This is equal to 20 mega electron volt. Thus the kinetic energy of an electron must be greater than 20 mega electron volt to be a part of nucleus. That means if an electron be an constituent part of a nucleus, then the electron must possess an energy equal to 20 mega electron volt. Experiments show that the electrons emitted by certain unstable nuclei don't have energy greater than 3 to 4 mega electron volt. Thus, we can conclude that electrons cannot be present within nuclei. Concept of Bohr orbit violates uncertainty principle. Now, from uncertainty principle, delta x, delta px greater than equal to h cut by 2. But energy E is equal to p square by 2m. So, delta E is equal to 2p delta p by 2m. So, 2 in the numerator and denominator will cancel out. It becomes delta E is equal to p delta p by m. P means mv, momentum, delta p by m. So v means delta x by delta t. So mm will cancel out, delta x by delta p delta t into delta p. So delta E delta t is equal to delta p into delta x. So delta E delta t as per energy time uncertainty, it is equal to h cut by 2. Now come to this part. According to the concept of Bohr orbit, energy of an electron in a orbit is constant. That means E is constant, means delta E is equal to 0. So from this energy time uncertainty, if delta E becomes 0, so delta T becomes infinity. All energy states of the atom must have an infinite lifetime. It's true. But the excited states of the atom have lifetime 10 to the power minus 8 seconds. It is finite. The finite lifetime delta T gives a finite width. There is a finite width uncertainty to the energy levels. Now let us consider few problems. The first problem is why in the case of moving electrons quantum mechanics is used, but for a moving car we use Newtonian mechanics. For an electron of mass, so we are considering it as ME, M suffix E, moving with velocity VE. The position momentum uncertainty relation is delta x delta px greater than equal to h cut. So px means here for electron Me delta VE greater than equal to h cut. So delta x delta VE greater than equal to h cut by M. H cut, its value is h by 2 pi is equal to 1.054 10 to the power minus 34 joule second. Now we have already done this one in de Broglie hypothesis. For an electron moving with velocity 10 to the power 6 meter per second and its mass is 9.1 10 to the minus 31 kg, the calculated value of lambda will be 7.3 angstrom. If the electron is moving with the velocity of light 10 to the power 8 meter per second, then it will be 730 angstrom. This value is a measurable quantity. But when a car is moving, suppose the car, its weight is mass is 1000 kg, it is moving with 100 meter per second, then its wavelength becomes 6.6 to 10 to the minus 39 meters. Its range is very small, very small. It cannot be measured. This wavelength cannot be measured. But this can be measured. If we consider 10 to the power 6 meter per second velocity of the electron, then it is 7.3 angstrom. If it is 10 to the power 8, then becomes 7.3 into 10 to the power minus 2 angstrom. This is a measurable quantity. This is a measurable quantity. Now come to this position. So here also this is 7.3. It's a measurable quantity. So equation 1 holds good. This equation 1 means this equation delta x delta Vx holds good for microscopic particles like electron in quantum mechanics. But for moving car, m is very high, so h by n is almost equal to 0. So delta x delta Vx almost equal to 0. So the wavelength lambda is so small that it cannot be measured. So in the case of moving car, the position and momentum can be measured. Moving car can be measured accurately. The result from equation 2, this is the equation 2, is true for macroscopic bodies in Newtonian mechanics or classical physics. Come to the next problem. Why in case of macroscopic bodies uncertainty principle is not relevant? Same answer can be given from the previous one. Delta x delta px greater than equal to h cut, that means h by 2 pi. So again delta x m delta Vx h cut by h by 2 pi. So delta x delta Vx greater than equal to h by 2 pi into m. For macroscopic bodies, m is very large in comparison to h. So the product delta x delta Vx is very small, tending to 0. This means macroscopic bodies possess the finite, tending to 0 means it is finite. So it possesses the finite position and momentum, which is in contrary to the Heisenberg uncertainty principle, which states that it is impossible to determine the position and momentum simultaneously. But here it is finite, it is possible. So it is in contradiction with the Heisenberg uncertainty principle. That's why uncertainty principle is not relevant for macroscopic bodies. Come to the next problem. It states that a particle of mass m constrained to move in one-dimensional potential box and trapped in an infinite potential well of width a. Width of the potential well is given as a. Estimate the ground state energy from uncertainty principle. Sketch a graph of this energy with width a. That means width of the well is a. From the uncertainty principle, we know that delta x minimum, delta x px minimum is h cut by 2. So delta px minimum is equal to h cut by 2 delta x. So delta px means m delta vx minimum is equal to h cut by 2 delta x. So delta vx minimum h cut by 2 m delta x. So this delta x is the width. This is equal to a. So this becomes h cut by 2ma. Now E minimum energy is equal to half m delta Vx square minimum. So this delta Vx square means h cut square by 2 square means 4 into m square a square. So m into 4m square a square means 1 by 2 is this. So this is h cut square by 8 m a square. So this is the energy, minimum energy. Now, if we plot, this is the minimum energy, h cut square by 8 m square. if we plot the energy minimum, that is the ground state energy, with A, then with the change of A, then A increasing means E will decrease more. This is the nature of the curve. Here the minimum energy is the ground state energy, and which is equal to h cut square by 8 ms square, and can be written as E ground is equal to this, and the variation is this. Now another problem is the atom in a solid possesses a certain minimum 0 point energy even at 0k, while no such restriction holds for the molecules in an ideal gas. Use uncertainty principle to explain this statement. We know that the lowest energy of any physical system at absolute zero temperature is almost equal to 0. This means that the kinetic energy of the system even at 0 Kelvin is finite and not 0. This energy is 0 point energy. Consider a particle of rest mass m0, and it is restricted to a linear dimension L under the influence of a potential. So position uncertainty is delta x is equal to L by 2. So it can be found anywhere within the region, in this region, L by 2 region. So from uncertainty principle, delta x delta px minimum, delta x max delta px minimum is equal to h cut by 2. So delta px minimum h cut by 2 delta x. So h cut by 2 delta x means L by 2. So this becomes h cut by L. So delta px minimum is equal to h cut by L. So the minimum kinetic energy E min is equal to p square by px square by 2 m0. Here we have calculated delta px minimum is equal to h cut by L. So putting this here, px square means, that means considering delta px square by 2 m0. So h cut square by L square, denominator is multiplied by 2 m0. So E minimum is equal to h cut square by 2 m0 L square. The minimum kinetic energy is finite and not 0 when the particle is confined to move in a finite region. But in the case of ideal gas at 0 Kelvin, gas molecules can move anywhere. So the position uncertainty delta x is 0. Here it is not L by 2. This is delta is tending to infinite, almost equal to delta is infinite, simply infinite, as it can be found anywhere from minus infinite to plus infinite, not minus L to plus L. It is minus infinite to plus infinite. Thus delta px minimum is equal to h cut by 2 delta x max. So if it is infinite, then this becomes 0, and the minimum kinetic energy E min is equal to px square by 2 m0. So delta px square by 2 m0, delta px square is equal to 0. So this E minimum is equal to 0. It means that no restriction in position holds for the molecule in an ideal gas. In case of ideal gas, the minimum kinetic energy is 0.